Alright, so we'll start in a few minutes. I'll just let people kind of stumble in or whatever. Whatever terminology you want to use. So Zach, what do we call today? I was thinking like pi minus 1 over 100 day? Or what? Thanks, Rex. I like, what was Zach doing? Like the floor of pi. What is pi minus 2? Hello. That's Mr. Pond. You can call me Matt too. Doesn't matter. It's tilde pi day. Yeah, it's close enough. You know, it's within epsilon, right? Yeah, mathpond. Yeah. I think there is an account called mathpond though, so I couldn't even get that one. Not that I would want it, but. Every day is pi minus epsilon for some epsilon. That's true, yeah. That's what I was thinking. That way you can kind of just always get away with it no matter what. Yeah, I know. Someone's probably trying to hold the account for some reason. I feel like it's like everyone buying those domain names back in like 2000 because they think someone's gonna want to buy it from them. Alright, I think we'll start soon. Yeah, it's about 4 o'clock. So yeah, to people in, I guess, where would it have to be? Like Japan? Maybe, where is it Pi Day so far? I would be shocked. E to the 2i pi. Okay. Let me turn this music off. Yeah, it's a good time. Oh, Dr. Gold is going right now? Okay, yeah. Well, I guess it's probably going to be popular on the math channel for the next 36 hours or so, right? I'm going to do just basically like normal stream. Maybe I'll do something special tomorrow, like maybe a little bit of extra exercises on the board or something. Haven't really thought about it too much. So I think when I was younger, I was never a big Pi Day guy because I was always like, oh, E is better. I was a E better than Pi guy. But now I think as I'm getting older, I'm maturing into a more love of the Pi Day celebration. Wait, Dr. Gold is in Japan? I haven't been doing much math. Been taking a break from school since I have debt. Oh, debt. Yeah. Yes. We are all familiar with the people in academia, at least, are familiar with the debt and bills for sure. Which one is higher, e to the pi or pi to the e? Yeah, that's definitely the most important question. No, I don't know. But yeah, let me just jump into the math a little bit. So I realized the exercise I did, I was talking to Rex about it. I completely messed up one of the exercises from yesterday. So I want to clear my name on that one first. Well, not first, but we'll talk about it after we talk about these Cauchy integral theorem, which is basically the way I was supposed to do the problem, but I was trying to do it without it. But I figured out it was kind of hard to do without it. Yeah, debt is the American dream, exactly. Um, right. So let's first look at this lemma. So we're talking about complex analysis in general, right? Um, so this is one of the first theorems you learn in the class. It's kind of like a fundamental theorem about learning to think about holomorphic functions in general, I think. You know, it's not the fundamental theorem of calculus. It's not the fundamental, well, the Cauchy integral formula basically is the fundamental theorem of calculus. But, right. So we're talking about Cauchy integral formula and theorem. Oops, formula. Let's write it this way. Oops. Yeah. Okay. Right. So what is the idea of the theorem? Once we get to harmonic stuff, there's very similar situation with harmonic functions where sort of like you can define the function at a certain value as some sort of like average of an integral around a circle. So this is very much of the same flavor. So the first lemma in the section, I think this is like 2.4. Yeah. Okay, so the theorem says if we have a line integral, so we've been doing these complex line integrals where we, parameterize a path and then take this, notion of complex integral around that path. So this lemma says if we have the boundary of a disk of radius r around some point, so let gamma be, boundary of this disk. Sometimes I'll write it like this with like a boldface D. So some point with some radius r. And then the important part of this theorem is that we pick a point that's on the interior of the circle. So we can't just pick an arbitrary point, it has to actually be inside. Actually, if we pick it outside, then I think the integral is just 0, so it doesn't really tell us much. But we need to pick this point I'm about to write, z, and let z be inside here. So be any point. So just pick any point inside the circle. Then we have this integral formula for, well, actually, no, not for the function, but the lemma is just for this particular integral. So it's going to look like the Cauchy integral formula, except instead of on the top, this will be like a simpler version. This one just has a 1 on the top instead of normally you'll have like f of z up here or f of zeta on the top. But here, this one, it'll just be 1 over something. And now on the bottom, we'll have zeta minus z. Or actually, yeah, that's right. And the lemma says that this integral is equal to exactly 1. So, oh yeah, let me write a little gamma here. Okay, so boundary of this, sometimes the boundary will write like a little d here for the boundary, but since I already wrote boundary here. So this integral is like, we're integrating around the outside of this circle. This is a circle of radius r. What would a triple integral be? A complex shape in 3D? Depends on what you mean by a triple integral. Are you talking about a triple complex integral? Because then you're probably talking about integrating over like a 6-dimensional domain or something, some subspace of that. But yeah, let's the multivariable complex stuff is a lot more complicated, so I don't want to get into that. Let's just focus on one complex variable. So yeah, this is the main statement though, if you're a little confused or you can't see it. Again, just we're taking a line integral counterclockwise. I guess I should specify that too. I believe it's counterclockwise. We're going around this way. And if you go the other way, you just get the negative of the integral, so you would get -1. But let's just assume, I believe it's, the theorem says that it's counterclockwise line integral. And so this is basically the Cauchy integral formula for the f of z on top is the constant function of 1. So you want to think of this as the value of the constant function at the point z. But no matter which z you pick, the value of the constant function is just 1. So, yeah. But more generally, the theorem we're about to state, you have some arbitrary holomorphic function on the top, f of z, or f of zeta. Sorry, this should be, should be more specific. This should be d zeta. So you're not integrating with respect to the z. Z is just picked inside the circle, but this is your integration variable. Yeah, that's more complicated than I thought. Yeah. So once you know this maybe if you've taken like a real, a real variable, multivariable, real calculus. I don't know. Real. So like when you have three, two or three real variables, the spaces that you can integrate over also get more complicated. So you have to start, you can have these like polar regions that you can integrate over, and then you need to change coordinates, and you need to, multiply by this Jacobian. So whenever you increase the dimensions of the space that you can integrate over, it's going to naturally get more complicated, even to just describe the, submanifold that you might be integrating over, or subdomain or whatever. Okay. Yeah, so I'm not going to prove this lemma, but let's just write down a very similar statement here. So it's basically the same statement. Actually, yeah, let me not even erase this because I don't want to waste too much time rewriting everything. But we also have a theorem here. This is the next theorem, the Cauchy integral formula. And that says that basically the same thing, but on the top here you have f of zeta. So this is Cauchy integral formula. This is like the next page, I think. 2.42. Okay, yeah. So the only addition that we're going to add here is now we're going to have a holomorphic function that's holomorphic on some closure of this disk. So it needs to be, the closure of this disk needs to be inside some open set U, and the function needs to be holomorphic on that open set. So that's what we're sort of adding in here. I could probably write that right here. So f is holomorphic on U. I can write that like this. F is like O of U, holomorphic on U. And also the boundary of this disk, the closure, is inside of U. Okay, so that's basically the only two things we're adding to the last lemma, and the only thing we're changing about the formula is that instead of on the top being 1, now we have a more general formula, which it could be any function of zeta, as long as that function, again, is holomorphic on this open set. And then instead of it being equal to 1, it's equal to the value of the function at the interior point z. So this is just equal to f of z. But again, all the hypotheses are the same, so you have to pick this point z on the interior of the disk, and the only thing we're adding is, again, this the closure of the disk needs to be fully contained inside of the open set U, where f is holomorphic on the entire U. Okay, so this is like a weird formula. It's sort of saying like you don't really need to know what the value of the function is at the point z. You can sort of get it as like an estimate or some sort of like averaging, which, an integral is some sort of average in some sense, right? Like, except we're dividing by, instead of a real number, we're like dividing by this 2 pi I. So you can think of this as like sort of like some sort of complex average where we're taking this integral around the boundary of the disk, and this interior point just happens to be equal to this sort of like complex averaging thing that you're doing here. Why choose XC? Yeah, that's just the book. That's I don't know. That's complex lore, I guess. I don't know. They love picking a letter that's hard to draw. It's not my doing. Yeah, mathematical community, exactly. Yeah, it's not my choice. I would probably just pick like W. I don't know why we don't use W more. I feel like W is a good complex number. Z, W, maybe what else is good? Yeah, or you can always throw in like, tildes or stuff like that. Um, okay, yeah, so Cauchy integral formula, it's some sort of statement about the value of this holomorphic function at some interior point of this disk is equal to this sort of averaging process where we integrate over the boundary of the exterior of the disk and then sort of divide out by the average, which is 2 pi I. Okay. Yeah, so this one's not so easy to prove, I think. Yeah, I'm not gonna try to prove this because I think it would just take like hours to probably explain fully. But I did want to make the connection to the harmonic functions where you do have a very similar theorem for harmonic functions where like the value of a harmonic function at a certain point is equal to like the average where you take an integral around some circle around that point and then you divide out by the I think it's like the radius of that circle. Or no, I'm probably saying it wrong. I think yeah, it's something like that. Maybe somebody can look it up and help me in the chat. 2 pi I times winding number in general. Yeah, it'll be for the yeah, if the well, specifically for this curve, yeah, it would be like how many times you go around the circle, but for a general curve that goes around Z, yeah, it would be basically how many times you're wrapping around this point Z. That's what the integral will be. Since we just wrapped around it one time, then you just get 2 pi I, and then you divide out by 2 pi I, you just get f of Z. So in general, when you do this integral, you're going to get 2 pi I times the value of the function. So it's kind of like maybe a little bit unexpected of a result. But remember, I think we were talking last time about how this integral for a holomorphic function, well, you have to be a little bit careful about this statement, but there's usually no homotopic difference between integrals over curves that are homotopic. So if I take one curve that can be continuously deformed to another curve, and the function is holomorphic on the complete interior of that movement, then you should get the same integral. So this is sort of something of that similar flavor where it doesn't matter which interior point we pick Z, we sort of get the same integral. Well, I mean, depending on Z, we're getting a different function value here, but it's sort of like, that's why I say it's like similar flavor. It's not the exact same statement, but yeah. So yeah, in general, you will get the winding number. You could, just to go on like a little bit of a tangent here for a second, you could have a more complicated curve. Like let's just kind of draw something that is possible. So let's say we had the same integral, f of zeta minus z d zeta. Now let's say zeta is like some weirder curve where we go like this, right? And let's say like this is the point Z on the interior of the disk. Let's just say like the disk looks something like that. Right, so now, yeah, like Zach is saying, like you're going to get however many times we wind it around this point Z. But yeah, that's not really part of the theorem. That's sort of probably a more general statement. To prove that, I'm not sure exactly what type of, well, I guess, yeah, you could just say it's homotopic to the path that goes around the circle exactly 3 times, and then that one you could count explicitly as long as Z is like in the middle of the circle exactly. So in general, you get this result where this is actually equal to like, well, yeah, you'd have to actually divide out by like some multiple of 2 pi I times, I guess, yeah, the winding number. So how many times we winded around this point Z before we matched back up at this point for the integral. would be f of z. I think, yeah, because you should be just getting multiples of the integral every time you go around. Right? Yeah, I'll be a little careful. I think that's correct, but let's wind him up. Yeah. Sorry, I'm still thinking about this. Yeah, I think that's right, but I'll put an asterisk there to be careful. Okay. Right, so now that we've talked about these complex line integral theorems and formulas, or I haven't talked about the theorem yet, but I want to go over that example I did yesterday because I did it completely wrong, even though I got the correct answer. So that's probably the worst thing you can do in math. You don't want to do a problem wrong and get the correct answer because then you think you did it correct, right? So let's go back over that problem. I think it was problem number 18 in the end of the section. I thought I was trying to do it without, I thought I was trying to do it explicitly by parametrizing the curve and then, doing some algebra. But I think I realized pretty shortly that that wasn't going to happen. So then I tried to do some algebra trick and I actually made a mistake. So I want to just correct the mistake really quick before we go on. And we can actually use the integral formula that I had before without the winding number, just the regular theorem to solve that problem. So okay, so where is that? I guess I'll go back. Oh no, I didn't have it written down. I'll just take it out of the book. Are there any questions so far about the Cauchy integral formula, theorem? Well, we haven't talked about I wrote theory here, I meant theorem. Okay, so this is page 62. And again, this is this Green and Krantz book, complex or function theory of one complex variable. So page 62, 18, problem number 18, and this was part A. And yeah, if you were here yesterday on Wednesday, I completely messed this one up. So the problem says you want to compute an integral around gamma, zeta squared over zeta minus 1, d zeta, and then the curve gamma, this is like a circle of radius 5, I think, around the origin. In particular, notice that the point here is zeta minus 1. The point 1 is inside this circle. So that's the key idea here you need to know. And if you know that, then you can just use the formula we just had written down. Otherwise, if you try to solve this explicitly, because it's not like the point in the middle, it becomes a little bit more difficult to solve explicitly like we solved the one for when it was just like 1 over z or 1 over zeta d zeta. So because this is sort of like asymmetric, that's what makes it actually hard to compute explicitly. But the formula tells us that we know what the answer should be, so we don't actually have to compute it explicitly. What's the 3, Rex? Okay, so basically this is just a Cauchy integral formula in disguise. We have a function on top, it's zeta squared, and then we have zeta minus 1, so it should be the function value at 1 times that 1 over 2 pi I that we had here. We need to move to the other side. So this should be 2 pi I times f of 1, where what's the, if anyone's paying attention, what's the function here 1? Or what's the function f here? And is it holomorphic? Because we can only use this formula if the function in the Cauchy integral formula is holomorphic, right? That was the statement. R equals 3. Oh, it was 3? Did I read it wrong? Oh, it is 3, yeah. Right. But either way, I mean, the integral's the same, right? We just need it to be, we need the point 1 to be in the interior, and it is. So that's fine. So actually, whether the circle is 3 or 5, the integral is actually the same. So that's kind of like one of the reasons we got the problem wrong in the first place, right? So yesterday we tried to do the long division, and then the problem with that is that you still end up with an integral in the end that is just as hard to compute. So it doesn't really help you to do the long division at all. But in this case, so f is the top function, right? So it's zeta squared. So it's, f of zeta is zeta squared. So f of 1 is just 1 squared. This should just still be 2 pi I times 1 squared, I guess, which is just 2 pi I. Okay, so that's really, that makes the problems a lot easier. You don't actually have to try to compute this explicitly. I think the book referred to this integral that you could actually do it explicitly, but it's just like a big mess. I sort of knew right when I started to do the problem that it wasn't going to be able to be done, but I was stubborn and I thought that it was the correct section. Right. So yeah, and I'll probably do a couple more of these from here, but a lot of these are very easy if you just have to pay attention to, sometimes they'll trick you and the point on the bottom isn't actually inside the disk, so that's a problem. Rex, since I know you're paying attention for sure, what would happen if I moved this point -1 outside the circle? Then what would the integral be? So instead of zeta -1, what if it was zeta -6? So same integral, but zeta squared over zeta -6. Yeah, that one's exactly 0. So why is that the case? So again, we're getting this discrete sort of behavior where, right as I move the point outside the circle, it immediately becomes 0, but right when it becomes in the circle, it becomes 2 pi I. So again, this is this topological behavior that really has to do with the domain that the function is defined in, whether you're puncturing this disk or not. And that's, you're changing the topology, and you get, this is actually a topological, I want to say invariant, but, well, it is in some sense. The integral is a topological invariant, yeah. Only the interior needs to be analytic. Right. Yeah, and if we're dividing by a function, this is just a rational function, and the pole is out. If the pole is outside the circle, that means if it's rational, that means it's holomorphic everywhere that it's defined. So it would be holomorphic on the entire part of the disk. The only part this meromorphic function is not defined is at zeta equals 6, right? So that's the only sort of point that you could have any issue at. What if the pole is on the boundary? If it's exactly on the boundary, yeah, then you have to also be careful. The integral might not even exist. It could just blow up. It could be a really bad point. It depends on how fast that point goes to infinity. So you could have an essential singularity on the boundary that could cause some issues, but I guess in this particular case, I'm not actually sure what happens if it's exactly on the boundary. I think I want to say if it's exactly on the boundary, then then the integral blows up, but I'm not 100% sure about that. I guess somebody could check it in Wolfram maybe. Can you give Wolfram complex integrals? Yeah, try this integral and then do a circle of radius 1. See what, I'm guessing it's infinite. I think maybe it's it'll say complex infinity or something. Because as you get closer to 1, I mean the function's blowing up, but I think it's blowing up quickly. I think you would have to divide by zeta -1 squared for it to not blow up. something like that. Yeah, I don't know. It's a good question though. Yeah, what if the pole is on the boundary? I'm trying to think, what if it is on the boundary? Yeah, I feel like the answer has to be that it blows up or something, because how can it go, like, it would have to flip between these two discrete values. So there has to be some sort of like jump discontinuity or something where it just blows up in between. I mean, I don't know for sure. That's not a proof, but I think it does blow up. It's a good question though. Pi times I times residue? What is that? Don't you mean 2 pi I times residue? But that's only if that's for the theorem to work, you need the point to be like completely inside the disk to use the Cauchy integral formula. 2 pi I cross res? Okay, yeah, let me just move on. Unless somebody has a question. But I'm just going to do part B just to make a point about these integrals. So same problem, 18, but part B. So now we have a circle radius 1. Oh, I didn't say the orientation, but it was counterclockwise for the last one. This one's also counterclockwise, so closed line integral, zeta on top, zeta plus 4, zeta minus 1 plus I, d zeta. And gamma, yeah, like I said, is circle of radius 1. So I guess you could say it's 0 to 2 pi given by, yeah, t goes to e to the it. Yeah, and we have the clockwise orientation. Okay, so yeah, then this is like what I was talking about before. So now we have a circle of radius 1, except neither of these roots on the bottom, none of these poles are within that circle. So essentially this function is just holomorphic everywhere on the boundary, and actually even a little bit, there's even some buffer room on the boundary. So I think what are the poles here? So we have -4 is one of them, so that's like out here somewhere, all the way out in no man's land. You can't even see it on the camera. And then the other root, or the other pole here, is like, what is that? You gotta flip it, so it's like 1 minus I think. So something like somewhere down here. So everywhere in the interior of the disk, including the boundary, and even like we could even draw like so even the boundary, but even the closure of the boundary, right? It's holomorphic everywhere in here. So if I take this integral, we have a theorem, Cauchy's integral theorem. Actually, I guess I skipped that one real quick. We'll go over that one right after this. But Cauchy's integral theorem says that if the function is holomorphic everywhere on the interior of this disk, and you're taking this counterclockwise integral around it, or I guess in this case it could be counterclockwise or clockwise, then the integral is just 0. But it has to be holomorphic on the entire interior of this disk, including the boundary, and some, has to be contained in the set U. So because of where these poles are positioned relative to this closed integral, like whether they basically there's zero. You can also think of it as there's zero winding number. So we're not going around these poles any number of times. So it's basically 0 times the residue at this pole and 0 times the residue at this pole, because it's, basically zero winding number. If I don't know if Zach's still there, but Zach was saying in general it's the the residue at the point times the winding number, right? Times 2 pi I. That's what we got before, but if we're not going around the pole any number of times, then the winding number is just 0. So that's another way you can think of this. So this whole integral is just 0. -4 and 1 minus I. Yeah. Yeah. Okay, and how do we know 1 minus I is outside this disk? Well, this disk is of radius 1. And this point has a modulus of square root of 1 squared plus 1 squared, right? So square root of 2. So absolute value of 1 minus I is square root of 2. And so that's bigger than 1. So that just tells you this point is slightly outside this circle. Yep, yeah, so integral is 0. And that's the statement of this Cauchy integral theorem, except wait. Yeah, so I thought we already proved that I feel like it's just fundamental theorem of calculus, but you need to make sure that for the Cauchy integral theorem, you have to make sure that there actually exists a holomorphic antiderivative. So I guess that's the important thing I should mention and talk about. So the Cauchy integral theorem is basically a statement like this, where we can guarantee that some integrals are 0 on these closed boundary curves, line integrals, as long as the function is holomorphic on the entire interior of the disk and there's no poles or anything, right? So in this case, these poles were outside the interior of the disk, so there was no problem. And the Cauchy integral formula then says that those types of integrals are just 0, because essentially we can just use the fundamental theorem of calculus, like we were talking about last time. Right, so the full theorem, and this one I think the argument is simple enough to just go over really quick. You're quick with the band. Right. Yeah, Cauchy integral theorem. So this is 2.4.3. Okay, so this says if we have a holomorphic function, if f is holomorphic on an open disk U, so again, I'll write it like this, holomorphic on an open disk U, okay. And if we have a closed, and we have a, right, and if we have a closed curve inside U is C1, so it's continuous and continuous derivative with the start and the end point equal. So with gamma at A equal to gamma at B. Then the theorem just says that the integral is 0. So. Okay. So basically, it's the fundamental theorem of calculus, but you need one extra thing to be true. We just need to prove that there's actually a holomorphic antiderivative to f of z. And that's only true because U is specifically an open disk. So if it was a more general open set, this wouldn't necessarily be true. And we already did an example where this was not zero when it wasn't an open disk, which was when we integrated 1 over z, and we did that circular integral, and we did it by hand, and we showed that it was 2 pi I. So here, this is really dependent on the open disk part, and that's because if it's on an open disk, then we know that there's an antiderivative to this holomorphic function. And because there's an antiderivative, then the integral of the derivative of the antiderivative, which is just this integral, has to be 0. So this is like a statement about, I forget what is it closed or exact, where the integral is 0? I forget. But yeah, this is basically just an example of the fundamental theorem of calculus, as long as you know that an antiderivative exists, which it always does on an open disk, but not on a more general set or domain. There's a special place in the sink of a complex plane for the spams. Oh, wait, what? Special place. Oh, like you're throwing them in the in the poles of the complex plane somewhere? Right. So again, the important parts of this theorem are the fact that the start and the end point are the same, and the fact that this is an open disk. That means that an antiderivative exists. And if the antiderivative exists, that means that this integral should just be the value at the endpoints subtracted from each other by the fundamental theorem of calculus. But, you know, if I'm subtracting one point from itself, that's just 0, right? So because these endpoints are the same, so if some antiderivative, let's call it like capital G, exists, then this integral should just be capital G at gamma of B minus capital G at gamma of A, but because they're equal, it's just 0. Okay, so are there any questions about this theorem? This is like, I guess I wanted to say surprising. It's not, I don't think surprising is the right word, but I guess it's like a nice result, because also what this says is that if I have two homotopic integrals, that they're actually equal to each other. And let me illustrate why that's true. And this is actually, I think, the most interesting result of this theorem, which is if I take two different paths here between 2 points, why is the integral the same? So let's say this is gamma of 1. I go this way, and let's say I take a different path, some other weird path, and I integrate over this other path, gamma 2. It's, let's say f is holomorphic on the, this whole set U. So this is like z naught, and this is just some w naught or something. So yeah, if anybody in the chat is paying attention, how can I use this theorem to show, let's say we have a holomorphic function on this entire open set U, and there's no poles or anything in the way. Why does the integral over the first path, gamma 1, going like up this way, why does that necessarily need to be equal to the other gamma 2 path, according to this theorem? So if this theorem wasn't true, we wouldn't have this homotopy property for the integral values. It's a very, very nice topological result, really. Because they homotopic, yeah, but I'm trying to explain why. So what about being homotopic? You can sort of see it just from looking at the picture. So why do these two homotopic curves, if they're defined on some simply connected set, or let's just say the whole set doesn't need to be simply connected, but the part that's we're looking at in the U part is simply connected. So let's just say there's no poles in U at all. So yeah, the curves are homotopic, but what about this theorem means that the values of the integrals need to be the same. That's the key idea. Well, that's true, but that's just the definition of homotopic. So yeah, they do deform to be each other, but let's look at why the integrals need to be the same according to this theorem. So actually, yeah, let me leave this picture up just to explain really quickly. So if I go around gamma 2 first, and then I do the negative of gamma 1, I actually have a closed integral. So really, let's say I go gamma 1, I'm going to write it as gamma 1 minus gamma 2. That just means I'm going first gamma 2, or sorry, actually I guess it's gamma 2 minus gamma 1. So first I'm going gamma 2, and then I'm going the negative orientation for the path gamma 1. Let's say it's f of z. Right, but this, by definition, this is the integral over gamma 2 path of f of z dz minus the path over gamma 1. Right, but then the Cauchy integral formula says this needs to be 0 because the function is holomorphic on the entire boundary and interior of this closed curve. Well, I guess technically the formula is only for disks. Oh, okay, yeah, I guess I'm kind of circular reasoning here a little bit, but yeah, okay, that kind of destroys it. Okay, yeah, so I'm basically just saying the same thing Rex has been saying, that because they're homotopic, then yeah, I'm basically just saying the same thing. Okay, well, yeah, that doesn't really work. All right, I guess, yeah, this is why you need to be a little bit careful when you talk about this stuff, because you can't just say that like one integral is equal to the, I guess, yeah, as long as the two curves create a circle, then it's true, because that's all the Cauchy integral formula is proved for. Trying to think. No, this still works, I guess, right? Yeah, sorry, yeah. The Cauchy integral theorem says any closed curve. It didn't need to be a circle. Right. So this is still good. Yeah. Okay, perfect. Yeah, so these two integrals need to be equal because the difference of them is 0 by Cauchy integral theorem. Okay, and this integral is 0 because the original integral is a closed curve, and the function is holomorphic on the entire u, and this is a closed curve inside of u, and there's no poles or anything getting in the way. Right, and that says that these integrals are actually equal to each other. So gamma 1 is a different path than gamma 2, but because it's a simply connected domain that we're looking at, u, then any two curves are actually homotopic to each other. And so this is another way of saying that the integral over these homotopic paths is they're actually equal to each other because their difference is 0 by this theorem. Yeah, because they flip signs. Yeah, exactly. Yeah, so the whole curve has the same start and end point. So the whole integral is 0. But the reason that we get this minus sign here is because we're flipping the orientation. So I sort of haven't gone over this, but you can prove that if you flip the orientation of the curve, basically like the derivative, remember the line integral is like a parameterization, and when you do the orientation the other way, you just pick up a negative sign basically. So yeah. So when I flip the orientation of the gamma 1 path here and we go the other way from W naught to Z naught, then if I combine the two, it's basically the sum of the two, but I need to flip the orientation, so I need to multiply this one by -1. So you can really think of it as like this integral plus this integral times -1, because the orientation flipped. Okay, so any questions? That's the Cauchy integral theorem. Very sort of not surprising result, but very interesting result in the fact that it's sort of combining complex analysis with this, topological result, which is a common theme with this complex stuff we've been talking about the last couple days. Okay. So yeah, any questions from the chat? I know as we go further and further, well, I guess it has to hit the hour first. I wonder if someone can look up where is it Pi Day now? I guess probably like Eastern Europe maybe. It's probably getting close to midnight over in England, right? What else do I have here? Oh yeah, we never went over the proof. Okay, yeah, let me write out the proof a little bit. I sort of gave you the idea of the proof, but let me write it out formally, because this one we can actually say something about, like, exactly without having to, take like 5 hours. What's your favorite kind of pie? Great question. I feel like I'm really into like a lemon, like meringue pie, like that really like sweet lemon pie. You know what I'm saying? But I'm really big like fruit pie, like any apple pie or anything like that. 8:48 in England, yeah, but that's pretty close, right? I don't know if midnight is like, yay, pie day. So, Zach, what do we do at? I guess it's 3.14 I guess we can do like, what's 15 o'clock? That's 3 o'clock. I guess that's when I normally stream anyways, right? Like, that'll be the pie hour. McDonald's pie? Okay. Okay, yeah. So let's write out this theorem. This one will be pretty precise. The reason I didn't go over the proofs of the other theorems earlier is because they're just sort of a little bit technical. You can look through the book for them, but yeah, I don't think I could do it justice in like a reasonable amount of time. So, I mean, even when I'm reading through it, it's very technical. It's hard to sort of follow. I'm sure I could follow it if I sat down for like a few hours, but I remember doing it in school, and it was also very complex, no pun intended. Right, so this is a proof of the Cauchy integral theorem. Again, this theorem just says if you're taking a closed line integral that starts and ends at the same point, and it's on the interior of an open set or of an open disk where the function is holomorphic on the entire interior, then this integral is 0. So that's what we're proving. This is like gamma, the path, integral over gamma, f of z. Z is holomorphic, then this is 0. We all grew up on the YouTube videos. Nobody reads books? I mean, I got a book right here, so counter example. Okay, so proof. So by they're citing a theorem. I'm gonna sort of justify again why this theorem is true, but I looked at their proof of this theorem. I think he's doing it in like a weird way because he's trying to do something sequentially in the book. But he basically says by theorem 1.5.3, there is an antiderivative on U for f because U is an open disk. And that's what this theorem is talking about. So by this theorem, there exists an antiderivative. So there exists some function let's say big F of z, such that big F of z derivative is equal to little f of z for all z in U. And then you're basically done. But the key here is this step, the fact that there exists a holomorphic antiderivative. Then you can just apply this fundamental theorem of calculus, and then everything works out nicely. You just get that difference being 0, like we were talking about before. But how do they prove 1.5.3? You can go back in the book and look. It's sort of weird, but I feel like there's a simpler proof, although I haven't really checked like rigorously if the argument I'm using, maybe I'm using some sort of circular logic somewhere or something. But in my understanding, we can just figure out what this holomorphic antiderivative is just by it is. I see why it's circular reasoning now. Yeah. I think I need to use the Cauchy integral formula to prove that the antiderivative exists. Once you know there's a holomorphic antiderivative, once you know this integral is O is 0, then you can actually define the holomorphic antiderivative as the integral over any path between 2 points. But I guess until you know that closed integral is going to be 0, then you can't use that to define the holomorphic antiderivative, or else you're assuming the theorem you're trying to prove to construct this f. So that's the reason if you go back in the book and you look at this 1.53, you'll see that the proof is like not super intuitive. It's not obvious like what they're doing or why they're proving it that way, but they do get the result that they need, which is that this antiderivative exists. And then we can just use fundamental theorem of calculus to say that the integral, this closed line integral, well, this is just the value of the antiderivative at the 2 endpoints. But just pick any point where it starts and stops. Right, so B and A, so it's like gamma of B, f of gamma of B minus f of gamma of A. So this is, if gamma of B and gamma A are the same value, then this is just f of some number minus itself. So this is 0. And that's the proof. Okay, so really the whole argument depends on this 1.5.3, which is a little bit of a technical result. They just say, if we're looking at this open disk and it needs to be a disk, and we have a holomorphic function, there's always an antiderivative that you can sort of construct, or it's sort of like an existence proof that says, this antiderivative definitely exists, and therefore, because of that fact and because of the fundamental theorem of calculus, we can conclude that Cauchy's theorem holds, that this integral is always 0. And again, now that you have that this integral is 0, so I think, once you have that this integral is 0, then you can prove that homotopic curves have the same integral. As long as they're homotopic to each other, they should give you the same integral. But that really depends on this result. So you can't prove this using that, and that would be sort of like circular. I can't argue with empirical data. I forget what you're referring to that with Rex, or what you were referring to there. I feel like it's harder to speak while you're streaming. Normally I have to think more about each word. Okay, any questions about this? So that's essentially the meat of this chapter, chapter 2. There's also an extension of the Cauchy integral formula to higher derivatives. So there's a very interesting result in the next section I was reading about the fact that if you have a holomorphic function, it's automatically, so it's C1 by definition, but you can also prove it's actually C infinity. It's C2, C3, C4. And then you can also show that the derivative of the holomorphic function is then also holomorphic. So basically it has infinite derivatives automatically. Just when you just assume C1 and you assume the Cauchy-Riemann equations hold, and you get infinite differentiability. So sort of That one I would say is a surprising result, because you wouldn't think you just assume the function C1, you assume the Cauchy-Riemann equations hold. It's clear, it's not obvious that the function has infinitely many derivatives, right? That seems kind of out there. Oh, the existence of my evidence. Okay, yeah. All right, yeah. So I think that's it for today. It's a good time to end. About an hour. If there's no more questions, but yeah, if you can take anything away from this lesson, just think of Cauchy integral theorem being like a special case of this fundamental theorem of calculus, and the fact that this holomorphic antiderivative always exists on open disks. But if we puncture the disk somewhere, especially inside this curve, then there doesn't need to be a holomorphic antiderivative existing. Maybe there is no holomorphic antiderivative, and this integral doesn't have to be zero then. But as long as it's defined everywhere in the interior of this disk, then any closed curve should have integral 0. Okay. Can we raid Steve from... I guess we could, yeah. I mean, why not? It is Pi Day. Maybe that'll get me some viewers. Yeah, let's raid him. What's his username? Is it just Stephen Wolfram? It's just Wolfram, or... I think it's just Wolfram, but I'm not sure. That's Stephen Wolfram? Okay, I'm just going to copy and paste it. Oh yeah, he might just deny, we might not be able to raid him. Hold on, I'll find out. Oh, no, it works. Okay. Alright, so let's go over to Stephen Wolfram, and, oh, wow. Yeah, we don't have very many viewers to raid, but oh well.